So the first application of lines and doing analysis on lines is trying to decide if a particular dot actually falls on a line. So in this case, we're trying to find if 4, 9, 3 lands on this line here. So the way we're going to start this is I'm going to end up putting the 4 in for the x, the 9 in for the y, and the 3 in for the z. And if I did that, I'm going to have a bunch of numbers over here, a bunch of numbers over here, all comma separated values. It's kind of a mess. So before I start, I'm going to take this line and I'm going to write it in the parametric form because it's a little less cumbersome for all of this algebra. So in order to write my parametric forms, I need to take all of the x coordinate positions and fill them out. So I'll have x is -4 plus 6n, y is 5 plus 3n, and z is 2 plus 1n. All right, good. So now that I have my parametric equations, I just have to start filling in my numbers and doing a little algebra. So 4 on the x is going to go in here. So what value of n would make this line have an x value of 4? Well, I'll kick the 4 over. 4 plus 4 is 8. And 8 divided by 6 reduces to 4/3. So what I just figured out then is that if I make the parameter 4/3, so if I go to this dot and take 4/3 of a step along this vector, I should end up with 4 as my x coordinate. Well, that's great, right? Because I need to have 4 if this point is on the line, but it's not enough. I need my x to be 4 and my y to be 9 and my z to be 3. So I've checked it for x. I'm going to check it for y. I'm going to take my y value, 9, and use the parametric equation for y is 5 plus 3n. Bring the 5 over. 9 minus 5 is 4. And 4 divided by 3 is n. Now, that's very encouraging. 4/3 of a step along this vector gets me to an x value of 4, which I need. 4/3 of a step along this vector from here also gets me to a 9, which I need. The only thing that remains is whether or not the z value will actually line up. So I'm going to do the same process, putting the z coordinate into the parametric equation for z. So 3 equals 2 plus 1n. Bring the 2 over. 3 minus 2 is 1. So n is 1. Well, there's my problem. I don't have a match. These two match, but it's not enough. This one doesn't match. Therefore, 493 is not on the line. And in case you don't trust me, just to check it, I'm going to take 4/3 and I'm going to put it in here and see what happens. So x, y, z would be -4, 5, 2 plus 4/3, 6, 3, 1. So x, y, z would be -4, 5, 2 plus 1/3 of 6 would be 2. 4 of those would be 8. 1/3 of 3 is 1. 4 of those would be 4. And 4/3 times 1 is 4/3. So adding them together, -4 and 8 is 4. 5 and 4 is 9. 2 and 4/3, well that's 6/3 plus an extra 4 is 10/3. Now, if you look what happened, I was checking the point 4, 9, 3, and I got the 4, and I got the 9, but it's in the wrong place in Z. So this line that goes off through space, I was able to find a dot at 4, 3, but when I checked the Z coordinate, it was too high. So all you need to do to check, I mean, this wasn't necessary, this was just to show you what happens when you use this value in this equation, is to take your parametric equations, plunk in the coordinates of the point you're trying to check, work through this process, and if, and only if, you get the same number for n in all three calculations, that point is on the line. If even one of them is different, then that point is not on the line of coordinates here. I want to check if this dot falls on this line. So these coordinates are going to go into my x, y, z here, which would be easier for me to do if I had it in parametric form. So I'm going to do that first. X is 1 plus 4n's. Y is 3 minus 6n's. And Z is negative 5 plus 2n's. All right, so put this x value in for x. 11 equals 1 plus 4n. Bring that over. 11 minus 1 is 10. 10 divided by 4. That reduces to 5 halves. All right. So in order to get to this location on this line, I have to take 5 halves of a step along this direction vector. Okay. Let's try the y coordinate. Negative 12 goes here. Bring this over. Minus 12 minus 13 is minus 15. Minus 15 divided by negative 6. This divides evenly by 3, as does this. 15 divided by 3 would be 5, and 6 divided by 3 would be 2. So 5 halves. Now that's encouraging. I have a match on x and a match on y. But that's not enough. I have to make sure it matches on z as well. So even though this is encouraging, I need to check that last coordinate. So z, 0, has to go in for here. So bring the 5 over. Divide both sides by 2. And there you have it. So I have a match in all three coordinates, which is telling me that if I took 5 halves of a step of this vector from this place, I will end up at 11, negative 12, 0. So that's it. We're done the question. So because they all match, negative 12, 0 is on the line. All right, and that's it. Basically, you're just taking coordinates, popping them in, and seeing if you can find a location on that line where all 3 coordinates would happen to line up. Okay, so I have line 1 starting at this particular location and then jumping as many times as you like along this vector. And I have line 2 starting in this location and jumping as many times as you like on this vector. And I want to know if they cross. So notice it says determine the point of intersection between these lines if it exists. So here's the neat thing about lines in 3 space. If you can imagine that this line is, this finger is a line, and that this finger is a line, right? And I hold them like this. Now if you're staring at that from your computer screen, it looks like my fingers are crossed. But the neat thing about 3 dimensions is that if I rotate, you can see that those lines are not touching each other as long as you look at them from the right direction. So what we need to decide is if these lines are actually in contact with each other, or if they're able to sort of pass above or below one another. So how are we going to do that? Well, when you were trying to test dots on lines, you just substituted in the x, y, z values into the equation of the line. Well, we're going to do that here as well. And in the dot question, it was easiest to use parametric equations, so we're going to do that again as well too. The thing I have to keep in mind though is that this line, I can take as many jumps of this as I want, and I can take as many jumps as this as I want, and these aren't going to be the same number. So I need to change this counter so I can keep them separate. So I'm just going to choose a different letter. I'm going to choose P there. So by the time I'm done, I will have figured out how many jumps along n I'll have to take, and how many jumps, p number of jumps I'll have to take along this to get to the place where these lines cross, if it exists. Alright, so continuing from there, at the point of intersection, the x-coordinates of these two lines have to match. So the x-coordinates of line 1 have to match the x-coordinates of line 2. So the x-coordinates for line 1 are -4 minus 5n's. And for line 2, they're -5 minus 2p's. So I'm going to just leave that for a second. At that point of intersection, the y values must match as well. So y values from line 1 would be -1 plus 2n. And for y2, they're 0 plus 1p. So I'm going to need a bit of substitution elimination in order to finish this, because I have 2 sets of equations in 2 variables. So if I just scan that, I have a lonely 1p sitting here. So that's the one I'm going to take advantage of. So if well, -1 plus 2n is worth a p. I'm going to try and get the p's by themselves here. So I'm going to take this -5 and kick it over. -4 plus 5 would be 1. And I have -2p's here. I could make this -2p if I doubled everything and switched the sign. So double this and switch would be 2, and that would be -4n. Alright. Now, the trick here is if this thing is equal to -2p's and this thing is equal to -2p's, then I should be able to equate them in order to find the value of n. So if I do that, 1 minus 5n equals 2 -4n. If that's the case, I'm going to bring this 2 over here and this over here. So 1 subtract 2 would be -4n's plus 5n's. 1 minus 2 is -1, and 5n's minus 4n's is just a single n. So there I go. I've got the value of n. Now I'm going to take that thing and I'm going to drop it into any equation I like that has an n and a p in it so that I can get the value of p. Now I could put it here, I could put it there, I could put it there. I'm just going to choose this one because there's some empty space under it to work. If I drop that in there, 2 minus 4, I know the value of n now is -1 equals -2p. -4 times -1 is +4, and 2 plus 4 is 6. 6 divided by -2 gives me -3 as my value for p. All right. So what this is telling me is that if I go one step backwards along this vector from this point, and 3 steps backwards along this vector from this point, that I should get to the place where my knuckle is, where those two lines appear to line up. So what's left to check then is whether they're hovering over top of each other in Z or if they're actually in contact. So net, I use the x coordinates and the y coordinates parametric equations to get values for n and p, and then I'm going to use the z coordinate to check my work. So if these actually cross, then z1 has to equal z at line 2. The z coordinates for 1 are 10 plus 4 n's. The z coordinates on 2 are -3 minus 3 p's. Alright. I know the value of n is -1, so I'm going to put that in here. And I know the value of p is -3, so I'm going to put that in here. 4 times -1 is -4. 10 minus 4 is 6. -3 times -3 is +9. And 9 minus 3 is 6. So there you go. We have a match. All right, so if I put in -1 for n and I put in -3 for p, both of these lines will end up at exactly the same place because I will get a match in x, a match in y, and also a match in z. So I've determined, because there's a match, the point of intersection does exist. Therefore, point of intersection exists. When n equals -1 and p equals -3. Now, you notice that I was asked to determine the point of intersection between these lines, if it exists. Well, I proved that it exists, but I don't actually have the point of intersection yet. So I'm going to need a little bit of space, so I'm going to erase this. But while I do, I want you to think about how we're going to get the actual location of that point of intersection. And the trick is that I already know n and I know p. So all I have to do is pick one of these lines and drop in the appropriate number, and I should be able to, I will be able to get the location of that intersection point. So I'm just going to choose line 1 just for fun. So -4, -1, 10 plus, and n is -1. So my point then would be -4, -1, 10 plus negative times this would be 5, negative times this would be -2, negative times this would be -4. -4 and 5 is 1. -1 and -2 is -3. 10 and -4 is 6. Now notice, that's not an accident. So these two lines, I showed that they could cross, and now I've calculated that they cross at 1 on the x, -3 on the y, 6 on the z. Now, if you're the type of person who likes to be thorough and likes to know they're right, then you could take line 2 and do this again. and see if you get 1 comma negative 3 comma negative comma 6. So just to show that it works, I'm going to do that. If I chose L2 instead, negative 5, 0, 3 plus, and the p-value is negative 3 at the point of intersection of these things, negative 2, 1, 3, minus 5, 0, 3, plus negative 3 times negative 2 is a 6, negative 3 times 1 is a negative 3, and negative 3 times 3 is a negative 9. Minus 5 and 6 is 1, 0 and negative 3 is negative 3, 3 and negative 9 is 6, which again matches in the z-coordinate, and you can see that the x matches, the y matches, the z matches. So I went through this whole process and I checked to see if I could get a match. If I get a match, then the point of intersection exists. To actually find the point of intersection, I just need to drop a parameter into one of the original lines and find the coordinates that it happens at. Here we go. So I have a new pair of lines, and I'm determining the point of intersection between them if it exists. So just like in the last example, I need to equate my parametric equations. So if they cross, then the x value of line 1 will have to match the x value of line 2. So my x values for line 1 are negative 2 minus 2n. And for x2, they're 1 minus 1p. My y-coordinates also have to match at a point of intersection if it exists. The y values for line 1 are 1 plus 1n. And for line 2, they're 2 plus 3p. Alright, so I'm going to get this n by itself because there's only one of them. So take 1 over to that side. I end up with n equals 2 minus 1 is 1 plus 3p. Over here, I have minus 2n equals, bring that over, 1 plus 2 would be 3 minus 1p. I can get a match between these two things if I double this and make it negative. So negative 2n would be negative 2 minus 6p's. And like in the last example, if this thing is worth negative 2n's and this thing is worth negative 2n's, then I can equate them to determine the value then, or p, sorry. So 3 minus 1p would be minus 2 minus 6p. And we're going to bring this over here and this over here. So minus 1p plus 6p is negative 2 minus 3. 6 and negative 1 would be 5. Minus 2 and minus 3 is negative 5. So p would be negative 1. Alright. So I'm going to take this and I'm going to drop it into any equation with an n and a p, and I'm going to choose that one just because it's the simplest. So n equals 1 plus 3, and this p-value I already know is negative 1. So n is 1, subtract 3, n is negative 2. Alright, so 1 step backwards on this line and 2 steps backwards on this line will get you to that place where x and y line up. We just have to check and see if z's are actually matching or if they're hovering atop each other like the last example. So I'm going to get my z coordinates. Z for line 1 would be negative 5 minus 3n. Z for line 2 would be 1 plus 1p. I know that n is negative 2. And I know that p is negative 1. Negative 3 times negative 2 is plus 6. 1 times negative 1 is minus 1. So 6 minus 5 would be 1. 1 minus 1 would be 0. And these don't match. So what I've shown there is that there's no match therefore these are skew lines.